So we're going to cover these sections here. We're going to talk about the current electromagnetic equations as we learned it so far. And then Maxwell saw that there's a problem with Ampere's law and corrected that. And then we want to derive the wave equation in free space. And then we solve the wave equations. And then we get the speed of light, and we mentioned the starting point of the special relativity. Of course, I'm not going to special relativity, but I'm going to tell you what was the Einstein's clue to get to a special relativity. And then we want to describe the exact plane electromagnetic wave, which is like this. You have seen it probably before. There are several features in this electromagnetic wave. You see that this is moving at the speed of light, of course. And there is electric field and magnetic field. They are perpendicular to each other. And they are in phase. And they have the same wavelength and the same frequency. So why is that? You know, you have already seen this maybe, but I was always puzzled, you know, why they are exactly in phase, why it is like that exactly. So I didn't know. So I derived all the formulas, and now I'm going to show you why it is exactly like this. All right, so then we talk about energy of electromagnetic waves or light intensity, and then we talk about momentum of the electromagnetic waves, which gives you radiation pressure. If you have radiation, you have some pressure. Some scientists, some engineers are using that radiation pressure for space travel, because it's from the light of the sun. You can get some pressure on a spaceship and get acceleration with no energy being spent. So these are the topics. Now I'm going to start with Maxwell equations. At the time of Maxwell, the electromagnetic equations were, as we have seen so far. We had Gauss law, remember chapter 23, that says that flux through any closed surface, or E dot dA, integral E dot dA through any closed surface, is equal to the charge inside that closed surface divided by epsilon naught. That's Gauss law. And then we have Gauss law for magnetic field, but this side is zero because we don't have magnetic monopole. If there was a magnetic monopole, this would be here. But this actually given as the evidence that there is no magnetic monopole as far as we know it. And then Ampere's law, which says integral of B dot ds around any closed loop, or which we call Amperian loop, is equal to mu naught times the current passing through that closed loop. Okay, that's Ampere's law. We talked about it. And then Faraday's law. Faraday's law says the EMF, or integral of E dot ds over closed loop, any closed loop, is equal to negative of rate of change of the flux of magnetic field through that. And we discussed that in the last chapter, a couple of chapters before. This is Faraday's law. And then we have Lorentz force, that is electric force and magnetic force. Remember, electric force was Q times E. Magnetic force is Q V cross B. And some of these two are called the general Lorentz force. So this is what the equations were at the time of Maxwell. But then Maxwell realized there's a problem here. Ampere's law states that the line integral is in fact mu naught times the current going through any surface bounded by the Amperian loop. This is more general than you maybe thought, but this is there's an Amperian loop that we take B dot ds integral around that loop. That is equal to mu naught times the current through any surface that is bounded by that loop that we take integral in this case. All right, and this like that. This is the Amperian loop. Let's say it's a circle, and of course the flat surface that bounds by that, there's current going through it, and you can write this, and there's no problem here, right? But this can be any surface, can be a surface like this, like a fishnet, right? It could be like this, but then again, you see that the current passes through that as well, so no problem here. But Maxwell realized there is a problem with this form of Ampere's law. Why? He said that, what if the current is going to charge a capacitor like this? The current going to charge this capacitor, so the current stops here. And then if you take this surface, okay, the current passes through the surface and everything is fine. But what if this surface passes through the capacitor, passes in between the plates of the capacitor? If this happens, you see that this doesn't change, because the integral of beta ds is there, and we have some value here. But there's no current going through this surface. The current through the surface is 0. So that is a problem. The left-hand side is not 0. The right-hand side is 0. The left-hand side is like this. The current passes from Ampere's law. We get some integral of beta ds. But if you consider this surface, the left-hand side is non-zero. The right-hand side is 0. All right. So that's a problem. So how do we fix it? We know that the charge on the capacitor is Q and negative Q, and the let's say that the area, surface area of the capacitor plates is A, and then we know that this current that comes here changes this Q. So as from the definition, current is dQ over dt, is rate of change of Q, which is this Q in this case, Q of the capacitor. And then we know that we can write this in terms of the surface charge density. Remember, surface charge density is Q over area. Therefore, Q can be written as sigma times A. So we can write I equal to d sigma A over dt. And remember also that the electric field inside can be written as sigma over epsilon naught. Therefore, sigma can be written as epsilon naught times E. Okay? Sigma is epsilon naught times E, so we can write instead of sigma, epsilon naught E times A, rate of change. Okay? And then E times A is the flux. Electric field in here times the area is the flux of electric field through this surface. So we can write E times A equal to phi E, flux of electric field, and we can take the epsilon outside, and we can write this as epsilon naught, rate of change of flux of electric field through this surface. Okay? So Maxwell said that there is this also, which we call it displacement current. And Maxwell said that this needs to be added to this current. So the total current is some real currents of the flow of charges and some due to this displacement current. So which is because of change of electric field or change of flux of electric field. So he added this part to the I that is here, and now mu naught times this becomes mu naught epsilon naught times rate of change of flux of electric field through this surface. Okay, so in general, it could be some of that and some of this displacement current. So this is called Maxwell Ampere-Maxwell equation, because it is the combined work of Ampere and Maxwell. So now, if you look at the equations that we know now, has this term in it. This part was Ampere's law, but Maxwell added this term, and now we have this. Okay. And now, what happens in free space? Free space means there's some place that there's nothing in there, in just free space, and there's no charges. So if there's no charges, then means this Q and this current is 0. So we put those equal to 0, and we get to these equations. All right, so we have these in free space. This one just tells us that no matter what surface you take, there's no charge there. Therefore, the integral of E dot dA over the surface of flux of the electric field going out of the surface is 0. The same is for B anyway, in any case. But that's good, but it doesn't give us any relationship between electric field and magnetic field by themselves. But these two gives us the electric field, the relationship between electric field and magnetic field. So let's see what these imply. All right. So these are the two equations that relate these two quantities, electric field and magnetic. We want to see what these imply. So in general, we have the electric field. It's a vector field. So it means that at any point in space and at any point in time, there's an electric field that has three components, X, Y, Z, and each one of the components is depends on the three coordinates of space and time. All right. So this is the most complicated situation. And the same for magnetic field, has three components and each one depends on all the three coordinates and time. But we want to simplify this. This is way too complicated, but we want to simplify it enough to keep the features that we want to show, but keep the complications away. So we use a special case where the electric field has only Y component. So we throw out the X and Z component. And also the Y component doesn't depend on Y and Z. It means that it is the same on any plane parallel to YZ coordinate system, YZ plane. All right, so this is the planar or electric field. Okay, so we simplify that a lot. And also the magnetic field, because of the situation that we have here, we see that magnetic field should be perpendicular to the electric field. I'm not going to details of that here. The magnetic field has only Z component, and also it doesn't depend on Y and Z coordinates. It only depends on X and T. All right, so these are the special cases, and then we can write it like that. So we throw all those complications away. But because the electric field and magnetic field only one component, we don't need to write the indices. So instead of E, Y, and BZ, we just write E and B. Okay. And keep in mind that E is in the Y direction with J hat, you see, and B is in the Z direction. So let's work on this. So see what happens when we have this. So in this coordinate system, we have electric field in the Y direction and the magnetic field in the Z direction. And of course, if you go move parallel to YZ plane, everything is the same. The electric field is uniform in that plane. But if you go in the X direction, the electric field and magnetic field change. And of course, they change also with time. Okay, but they should follow, or they should satisfy these equations at all time. Okay, and all time at all places. So let's see what happens. Let's say we have this, excuse me. Let's say we have this rectangle that has a side, long side in the Z direction, and it is in the ZX plane, and has a width of delta X. And you see for this one, if you look at this, the flux of magnetic field through that is 0 because there's nothing, no magnetic field passes through this loop. And integral E dot ds is 0 because E is perpendicular to all sides of this. So E dot ds will be 0 at all points. So this doesn't give you anything, but it gives you that this one gives you some meaningful result. So this loop is starting at point X, has a width of delta X and has a length of L. And of course, it ends up at X plus delta X. And we're going to use that if we want to integrate over this counterclockwise, as you see. All right. Now, this one doesn't give you anything, so I throw this away, but see what happens to this equation. Applying this equation to the loop, what happens? First, we want to see integral of B dot ds around this loop, all right? So B is this way, could be the other way, but usually in the z direction. So if you calculate b dot ds on this side is 0, on this side is 0 because these sides are perpendicular to b, but on this side is non-zero, and it gives us b evaluated at this point at x plus delta x times the length, and there's a negative sign because we go this way and the b field is the other way. Okay, so negative b times l, b evaluated at x plus delta x times l, right? So this is the part of this integral that is on this side, and as I said, these two parts are 0, and then on that side, because we're going in this direction of b, b dot ds is positive, and the integral becomes b evaluated at x and t and times l. So it becomes plus b of x and t, b evaluated at x and t times l. This one is b evaluated at x plus delta x because we are on this side. Okay, so do you see that? Any questions? All right, so this is the line integral on this side, and according to this formula or this equation, this says that this should be equal to mu naught epsilon naught times rate of change of flux of electric field through this loop, and the electric field is perpendicular to that loop, right? So and electric field is kind of uniform in here. It changes a little bit from here to here, but in general we can say, and delta x will be set to approach to 0. So roughly we can say this electric field at point x and t times the area. All right, that's the flux. So we say mu naught epsilon naught times rate of change of electric field at x and t times the area, which is L times delta x. So it becomes this. Mu naught epsilon naught rate of change of electric field times the area, right? And then you see that every term has L. L can come out here. And then we have here, L can be factored and canceled. So L doesn't matter. And then we can bring this delta x out of this derivative and divide by delta x, all right? And we can write it this way. So on this side, we have mu naught epsilon naught rate of change of E at x and t, rate of change of E with respect to time. On this side, we can factor a negative sign, becomes B evaluated at x plus delta x and t minus B evaluated at x and t. So this minus and minus becomes positive that we have here, divide by delta x, all right? And then if we let delta x approach 0 and take the limit, this becomes the partial derivative of b with respect to x. And we have partial derivative of e with respect to t on the other side. And there's a negative sign here. Okay. And then we know b and e are functions of x and t. We can drop the dependence and we can write it simply like that. All right, so this says that rate of change of b with respect to x is equal to negative mu naught epsilon naught rate of change of e with respect to t time. All right, so this is what we get from this equation. So we can put that aside and then see what the other equation gives us. For the other equation to give us a meaningful result, we need to consider this loop. So the first equation, it gives us 0 for this one. And second, this one gives us 0 for the other loop. So we apply to this one. All right, so again, this starts from x, ends at x plus delta x, and it has a length L and width delta x. And then we need to calculate integral E dot ds over this counterclockwise. And that becomes E evaluated at x plus delta x times L. And then, of course, at time t, and minus E evaluated at x times L, right? So this is the line integral. The other side, you see in this side and this side, the E is perpendicular to the ds, so E dot ds is 0. So those two sides don't make any contributions to this integral, okay? And then according to this equation, this should be negative rate of change of flux of magnetic field. So becomes negative rate of change of B field times the area. And B is perpendicular to this one now, becomes B times area. Again, L can be canceled, and we can divide by delta X. We get to this. And again, as delta X goes to 0, take the limit, this becomes partial derivative of E with respect to X, and this side is partial derivative of B with respect to T. So it becomes like this, okay? And then we drop the X and T dependence because we know that. We get this one, and this is our second equation. So the two equations that we had in Maxwell equation in free space convert to these two equations, all right? So far we have this in free space. So let's see what we can do with that. We want to combine these two even further. Let's take the derivative of the first equation with respect to X and take the derivative of the second equation with respect to time. And the first equation becomes second derivative of E with respect to X equal to negative second derivative of B with respect to X and T. The second equation becomes second equation of B, second derivative of B with respect to T and X equal to negative mu naught epsilon naught, second derivative of E with respect to T, partial derivatives, all right? And then you see that these two are the same. And if you replace this by this one, negative of this one, negative cancels, you get this equation. You get second derivative of E with respect to X is equal to mu naught epsilon naught, second derivative of E with respect to T. So now we have an equation just for E, okay? This equation only involves electric field. These are electric field, magnetic field, electric field, magnetic field, but this is only electric field. Basically, we eliminated B in these two equations. So we get this. So let's put that aside. And then this time, we take derivative of the first one with respect to T, but the second one with respect to X. If we do that, we get the second derivative of E with respect to T and X, and the other side becomes second derivative of B with respect to T only. And the second equation becomes second derivative with respect to second derivative of B with respect to X equal to negative mu naught epsilon naught, second derivative of E with respect to X and T. And again, you see that these two are the same. If you replace this in here by that, you get negative and negative become positive. So you get another equation identical to the first one for magnetic field. You see these two equations are exactly the same. And one is for electric field, one is for magnetic field. All right. So let's see what happens with this. So these are known in physics as wave equations, but I want to show you how to get to the solution. Of course, I just give you the general solution that, and we check it that it works. Usually, when you have a this kind of relationship, second derivative with respect to X, second derivative with respect to T, the general solution is something like this. E equal to a amplitude E naught, which is a constant for us right now, cosine of some number times X, which is here, plus or minus another number times T. Okay, so this is the general solution of these equations. And now I want to show you why is that a wave and what are the characteristics of it. And B has exact same solution. So there's magnitude, we call it V naught, cosine of kx plus minus omega t. Now, first we look at the negative sign in here, and then we see what will happen if you have positive sign. So we'll look at the negative sign only. So let's look at the electric field first. we want to see if that satisfies the electric field, the equation. This electric field solution that we have should satisfy this. So let's see how it's satisfied. And if you take two derivatives of E with respect to X, so this is cosine of Kx and some T. So if you take derivative with respect to X, you can consider T constant. And then the first derivative brings a K here, and cosine becomes negative sine. All right. And the second derivative, sine becomes cosine and gives you another K. So this second derivative of E with respect to X becomes negative K squared E naught cosine of the same thing, right? So that's negative K squared E naught cosine of Kx minus omega T. And if you take two derivatives with respect to T, what do we get? The first derivative with respect to T gives you a negative omega, and the cosine becomes negative sine, right? So becomes positive omega E naught sine of this expression. The second derivative gives you negative omega, and then sine becomes cosine. And so you get negative omega squared E naught cosine of Kx minus omega T. All right. And then if you plug in these into this equation, it means that this should be equal to mu naught epsilon naught times this one. So this first one is equal to mu naught epsilon naught times negative omega squared E naught cosine of Kx minus omega T. All right. And then you see cosine of Kx minus omega T can be canceled, and negative sine can be canceled. E naught can be canceled. So we get K squared is equal to epsilon naught mu naught omega squared. So this is what we get for the solution. In order for this function to be the solution to this equation should be satisfied. Okay. All right, so let's put that in here because that's a condition for these K and omega. They are related like this. Okay. So now let's look at we want to find out what these K and omega are. We look at the function E, like this one, at a moment in time, say at t equal to t naught. So then will be E of x and t naught equal to E naught cosine of Kx minus omega t naught, right? So this is a constant. It is a function of x, right? T naught is a number. It's a function of x. It's a cosine function, right? So it's like this. E as a function of x is kind of like that. Now, from this crest to this crest, we call it lambda, which is basically if it's a wave, it becomes wavelength. And what is this wavelength related to anything that we have here? So when x changes from a, means this point, to a plus lambda, you see that this cosine function goes from +1 to -1 back to +1. So it means that the argument of cosine changes from 0 to 2 pi. All right. So if you see, if x changes from by a lambda, so argument of cosine changes by 2 pi. So it means that k lambda is equal to 2 pi. So k is in fact 2 pi over lambda. K is 2 pi divided by the wavelength. We call it wave number. And so this is what we find out. Now, if you, instead of looking at this electric field equation at the moment in time, let's look at it at a point in space, like x equal to x naught. If x is equal to x naught, then you put x equal to x naught, and it's a function of time. So it means that at one point in space, electric field oscillates by cosine omega t, right, with a phase, constant phase. That doesn't matter. It has amplitude E naught. So if you look at the electric field as a function of time, it gives you this. Okay. So means that one point in space goes up and down, up and down. I mean, the electric field goes positive, negative oscillates at that point. And the distance in here in time, of course, the time between this maximum to the next maximum is the cycle, which is the period of the oscillatory motion or the periodic motion. All right, and then when a t changes from this point to this point in time, the argument of cosine goes through the change of 2 pi. So in here, omega times capital T is equal to 2 pi. So omega capital T is 2 pi, therefore omega is 2 pi over T, and T is the period of oscillation. And you know that its inverse of that is frequency. So omega is 2 pi f frequency. All right. So now we look at the function at a moment in time again. Say at t equal to t naught, we have x of t and x naught. So it becomes a function of x again. So like that, we did that before. Now we want to see what happens if we look at this at a little time later. Again, that's lambda. At a later time, t, which is t naught plus delta t, what will happen? Okay, so now we put t equal to t naught plus delta t in here. So it becomes like this. So E at x and t naught plus delta t becomes E naught cosine of kx minus omega times t naught plus delta t. So just put t equal to t naught plus delta t. I want to see what does it look like. All right, we distribute here. And then now we have kx and delta t here. I want to write it in terms of x. If I put these two together and factor k, what happens is x minus omega over k times delta t, right? So E at x and t naught plus delta t becomes this one, which is k that times this quantity minus omega t. So remember in calculus, if you have a function f of x and you change x to x minus x naught, what happens to the diagram, the graph of the function? Does anybody remember?
It shifts to the right.
It shifts to the right by this quantity, right?
Yeah.
Very good, very good. So this is the same cosine graph shifted to the right by this amount, delta x, which is omega over k times delta t. So if you look at that, at some later time, you see that this is shifted. By how much? This much. And then this delta x is equal to the omega over k times delta t. And then you can divide by delta t. And so you see that delta x over delta t is omega over k. Therefore, it is the velocity of this of the wave. Wave is moving at the velocity v that's coming from omega over k. Okay, so these are known facts in physics, but I just wanted to show you how mathematically you see that. All right. So this is the velocity of the wave. So we have a wave as a solution of this. Okay, it's a wave equation, and the solution is a wave moving to the right. And what happens if I change this to positive? Then this becomes positive, this becomes positive, then it goes to the left, right? So now you know that you have these and you have these solutions. If you have kx minus omega t, this is a wave traveling or propagating in the positive x direction. And if you take a positive one, this is traveling wave propagating in the negative x direction. All right, so both of these are solutions of the Maxwell equations. Okay, any questions? All right, so we get back to this. Let's put that here. Now, what is V squared? V is omega over K. V squared is omega squared over K. But omega squared over K from this equation is 1 over epsilon naught mu naught. So this gives us the equation, the speed. V is equal to 1 over square root of epsilon naught mu naught. So the speed of this electromagnetic electric wave that you see, of course, magnetic wave is also identical with that. And the speed is this. This is a very important result. This is the Einstein's clue to come up with relativity. It's the starting point of special relativity. How is that? Let me show you. V is this. Then you can write, instead of epsilon naught, you can write 1 over 4 pi k. And that reverses, becomes square root of 4 pi k over mu naught. And then you can write the values of k and mu naught, 4 pi times 10 to the negative times 9 times 10 to the negative 9. 4 pi times 9 times 10 to the 9. This for k, 9 times 10 to the 9. Mu naught is 4 pi times 10 to the negative 7. 4 pi cancels. This goes up, becomes positive 7. So it becomes 9 times 10 to the 16. Under square root, it becomes 3 times 10 to the 8 meters per second. So this is the known speed of light. Known value of the speed of light at that time, they knew that before Maxwell. But when Maxwell calculated the speed of these electromagnetic waves, he realized that, oh, that is the speed of light that we know. Therefore, the scientists said, okay, so then light should be electromagnetic waves. All right. And then see what Einstein took from this. Einstein believed in equivalence principle that says all inertial frames of reference are equivalent. What does that mean? Means no experiment can be done in one inertial frame of reference to figure out from inside whether the frame is stationary or it is moving at constant velocity. Of course, if suppose you are in a spaceship and there's no windows outside and you're moving at some speed. If you don't look at outside, if you look at outside, you see other masses, other things are moving with respect to you. So you say that, okay, I'm moving. But if there's no window, how can you decide? How can you make an experiment that shows that you're moving? The equivalence principle says that there's none. There's no experiment that you can do to figure that you're moving, because all the physics is the same when you're moving and when you're not moving. Okay, all the physics is the same. So you cannot do that. So Einstein said, if the speed of light is determined by epsilon naught and mu naught, we can set up experiments in one frame of reference and measure these constants. So you suppose your frame of reference is moving and you set up an experiment, you measure epsilon naught and mu naught. And we should get the same values for this epsilon naught and mu naught, regardless of our state of motion. Otherwise, we can detect our uniform motion. So if we get a different number for epsilon naught mu naught when we are moving, then we can detect our motion. Therefore, we should not get this different number. You should get the same number according to the principle, equivalence principle. Therefore, the speed of light must be the same for all inertial frames of reference. And that is one of the postulates of the special relativity. So he put these two together and came up with postulates of special relativity. One was equivalence principle. The other one was constancy of the speed of light. So when I was in college or high school, I was studying special relativity, and all the books start with a experiment that's called Michelson-Morley experiment. Michelson-Morley, they performed an experiment that showed, because at that time, people thought that the light moves through a material called ether that is, everywhere. And then Michelson-Morley, they made an experiment to see that, okay, if the Earth is going this way at one time, it's going through the ether in one direction, and then 6 months later, the Earth is going in the other direction. So we should be able to detect when the Earth is moving through the ether. And they did the measurements, they did the experiment, they find nothing. They found that there's no detectable motion of Earth through the ether. But Einstein said that, when I read somewhere that Einstein said that he didn't know about the Michelson-Morley. And I was confused because every relativity book starts with that experiment. And when I read that and Einstein said, I didn't need Michelson-Morley experiment results, I was confused. And now I see that, Einstein got it from this fact. He didn't know, he didn't need the Michelson-Morley experiment. All right, so that is the start of relativity. I'm going back to the electromagnetic waves again to see why it is exactly as you saw in that animation. All right. The wave solutions of E and B are both this form, but there's no reason for, until now, there's no reason for the wavelength. Remember, K was 2 pi over lambda, and omega was 2 pi over T or 2 pi F. This omega is angular frequency. This relates to wavelength. So, so far, there's no reason for these solutions to have the same K and the same omega. Okay, the electric field can have some value, some wavelength and frequency for itself. Magnetic field can have another wavelength and another frequency, right? And can be some phase between them. So let's see what happens, but they have to satisfy the Maxwell equations that we derived from the original integral form. These are the differential forms of Maxwell equation. So this is one of them. We verified that the rate of change of E with respect to X should be equal to negative of rate of change of B with respect to T. And also this one, you see here, it was epsilon naught mu naught, but we know that epsilon naught mu naught, the square root of that is 1 over C, and therefore epsilon naught mu naught is 1 over C squared, which is the speed of light, okay? So instead of epsilon naught mu naught, we can write 1 over C squared. So this is the differential form of Maxwell equations, and these two should satisfy this. So if it apply this formula, it says that the rate of change of E with respect to X, the partial with respect to X of E. So this is E, take partial derivative with respect to X, it gives you a K and negative sign, right? Negative K1 E naught sine of K1X minus omega 1T. And then that should be equal to negative rate of change of B with respect to T, okay? So here, if you take derivative with respect to T, it gives you negative omega 2, and then you get negative sign, and there's negative here also, there are 3 negatives, becomes negative, and then B naught omega 2 times sine of K2X minus omega 2T plus 5. And if you apply this one, negative 1 over C squared, rate of change of E with respect to T. So what is the derivative of E with respect to T? Becomes negative omega 1 E naught, negative sine K1X minus omega 1T, right? So there is negative here, negative from this one, and negative from the derivative becomes 3 negatives, gives you a negative. And omega 1 E naught sine K1X minus omega 1T, and 1 over C squared. And then the other side gives you derivative with respect to Tx of this one. So that gives you negative K2 B naught sine of whatever is here, right? Okay, so you see these have to be satisfied. Both of these have to be satisfied at all time and everywhere in space. So in order for that to happen, first of all, the sign arguments of sine and cosine should be the same, because otherwise one goes up, one goes down. They match at one time and they don't match at another time or another space. So the arguments should be the same. So we say k1x minus omega 1t should be equal to k2x minus omega 2t plus phi at any time, at any position in space. Okay. And then if you collect all the terms of x and all the time and separate phi, so it becomes you bring all of these on the other side, becomes k2 minus k1 times x minus omega 2 minus omega 1 times t plus phi equal to 0. But again, these should be satisfied for all x and t. The only way this can be satisfied is that k2 and k1 should be the same, omega 2 and omega 1 should be the same independently, and phi should be 0. All right, so k1 is equal to k2, and now we call it k because there's no 1 and 2, both of them are the same. And omega 2 and omega 1 is the same, we call it omega, and phi is 0. All right, so the electric and magnetic waves have the same wavelength and frequency. The electric and magnetic fields are always in phase with one another, right? So this is the proof that they have to be the same because they have to satisfy this equation at all time, right? All right, what else can we say? We look at, if we go back in here, let me go back in here. Now that these are the same, you can drop them and with the negative sign, and then k E naught is equal to omega B naught, right? So we have k E naught equal to omega B naught, and then E naught is omega over k B naught. But remember, omega over k was what? Was the speed of the wave, which is the speed of light. So E naught is c times B naught. And also from this equation, we say that from the other equation, k B naught equal to 1 over c squared omega times E naught. Again, if you look at B naught, solve for B naught. B naught is 1 over c squared omega over k times E naught. And omega over k is c, so it becomes c over c squared, which is 1 over c. Again, you have the same thing. E naught is c B naught, right? So E naught is equal to c B naught at all times. Amplitudes of E and B are related. Not only the amplitude, the instantaneous values of E and B are related by this equation. You can also show that. Okay, because if you put those, let's say E naught equal to C B naught, you see that E is also CB. Okay, so at all times they are related. So that's, now we get this, all the features of this electromagnetic wave. The two are in phase. They have the same wavelength, they have the same frequency, and they're moving at the speed of light to the positive x direction. All right? Any questions? All right, so this is wave solutions of Maxwell equations. All right, what about the energy densities? Remember that we said that when we have electric field, we have electric field energy density in space. And when we have magnetic field, we have magnetic field energy density in space, and we derive these equations, right? Both of them. And then we have this also, E is equal to CB for all of them, and C is 1 over square root of epsilon naught mu naught. Okay, we have all these. Now let's look at the total energy of electromagnetic wave. And first of all, let's look at the energy of the magnetic field. Magnetic field is 1 over 2 mu naught B squared. Instead of B, we can write E over C. So this becomes like that. So this becomes E squared divided by C squared. And then C squared, according to this, is 1 over epsilon naught mu naught. So we can send epsilon naught mu naught in the numerator. So you see that mu naught cancels, and you get 1/2 epsilon naught E squared. So the energy of the magnetic field, because of this and that, becomes the same as the energy at any point, the energy density of electric field. So that's U of magnetic field is equal to U of electric field. Means that the E and B have equal shares of the energy. Okay, an electromagnetic wave has energy. Half of it exactly is due to magnetic field. Half of it is due to electric field. All right. The total energy of the wave then is U, that is UE plus UB, which is 2 times UE. Instead of UB is the same as UE, we can say twice one of them. And that 2 times UE becomes just epsilon naught E squared. Okay. So the energy of an electromagnetic wave can be written, the energy density at any point in the electromagnetic wave is equal to epsilon naught times E squared. Okay, at any point, if you have electric field, you have that much energy of the wave. So let's see what else we can have. All right, this is showing an electromagnetic wave. See that again, E field that is in the vertical direction, Y direction, and B field in the Z direction oscillates and going in the X direction, right? And now we take a sliver here of a space, and that has a thickness dx and has area A. All right, that's like a cubic kind of thing. And dx is c dt, because it's one point that's moving with the wave. The energy going through area A during the time interval dt is the total energy between the two planes of volume dv. So this is the volume dv. We said that the energy that goes through one face of this cube or rectangular cube is in time dt is the total energy that is in this cube. All right. And dv is a times dx, but dx is c times dt. Okay, so it becomes a times c dt. And then du is the energy of the electromagnetic field density, energy density of electromagnetic field times dv. This is the energy. This is energy density times dv. So energy density is du over dv, means energy per unit volume. So du is u dv. And dv is written as dx times the area. So it is dv is this. We calculated already. U times that quantity. Okay. So du becomes that. Or instead of u, we can write this quantity, epsilon naught e squared, ac dt. And so the flux of energy per unit area, per unit time is du over dt, means per unit time, per unit area is this quantity. We call it S. Okay? Which is, you see, this was du. If you divide by dt, divide by area, what you get is epsilon naught c e squared. So that's that. You can write it this way. You can manipulate that. You can write epsilon naught c times e times e. We write one of the e's in terms of b. So e is cb, so it becomes c squared b times e. And epsilon c squared is 1 over epsilon naught mu naught. So it becomes like that. And epsilon naught cancels, get 1 over mu naught. B times E. This is the magnitude of a vector called pointing vector. So this is the magnitude of the pointing vector. And in fact, the pointing vector is defined like this. The pointing vector is a vector that is at any point the cross product of E and B and divide by mu naught. So look at that. For example, if you do E cross B from right-hand rule, E is up in this point. B is toward you, and if you do right-hand rule, turn your fingers from up toward yourself, you see that your thumb shows the direction of X. This is a pointing vector that is in the directional propagation of the electromagnetic wave, and it's defined like that. So what is the importance of this? The unit of that is also joule per meter squared. So this is repetition. The average value of the pointing vector is the light intensity, which is the power per unit area, or this joules per second is the power per unit area becomes light intensity, the average of pointing vector. So I is the average of pointing vector, or ERMS, BRMS, remember RMS values that we defined, becomes the average of these two becomes ERMS times BRMS divided by mu naught, and they are perpendicular to each other. So the cross product, magnitude of the cross product becomes just magnitude of E times magnitude of B, because sine of the angle is 1. All right, so becomes like that. And remember, in terms of the maximum values, RMS values are maximum divided by square root of 2. So we get a square root of 2 in the denominator for this, another square root of 2, you get a 2 in terms of the maximum, E naught and B naught over 2 mu naught. So it becomes 1/2 C epsilon naught E naught squared. And that is the light intensity, right? And I guess that, yeah, the light intensity is just the average of pointing vector, and it is joule per watt per meter squared of light. For example, the light intensity of the sun around the surface of the earth above the atmosphere is about 1300 joules per meter squared, watt per meter squared. On the surface, because some of it is absorbed by the atmosphere, is on average about 1000 watt per meter squared. All right, so for example, if you leave your car in the sun and it warms up, you see that it is depending on its area. If the area of the car is like what, 10 meters squared, it is like you have a 10,000 watt heater inside. That's why it gets hot, very fast. All right. Maxwell also showed that if a beam of electromagnetic radiation or light is completely absorbed by an object, then the momentum transfer is given by delta P equal to delta U over C. All right, that's the assumption of Maxwell. It may work. Using Newton's second law, we can calculate the force and the pressure. When the force applies on surface, there's pressure. We call it radiation pressure. And there's a device in every lab that shows that there is a pressure of radiation. There's something in a bulb. I don't know if you have seen it before. Have you ever seen something like that? If you shine light on it, it starts rotating, even though there's no, it is vacuum, there's no air in there, only light rotates that. All right, the force, according to Newton's law, is rate of change of momentum. So if delta dP is du over c, then F is dP over dt. So the average rate that energy is delivered to the object is related to the pointing vector by this formula. So S is equal to 1 over A du dt. We saw that. The radiation pressure P, assuming full absorption, is given by P equal to F over area. That is the normal definition of pressure, which is force divided by area. So if you have this divided by area and P is this, you see it becomes 1 over area. Instead of F, we say dP dt. And instead of P, we say U over C, right? Delta P is delta U over C, or P is U over C. So this becomes 1 over AC du dt, or the average of the Poynting vector divided by C. And the average of Poynting vector is the intensity, light intensity, I. So P, pressure, becomes I divided by C. So radiation pressure is equal to intensity of the light divided by the speed of light. So for example, if I said the light intensity of the sun's light is about 1,000, so 10 to the 13 here, divided by C, which is a large number in SI units. So radiation pressure of the sunlight, let me calculate quickly, very small, this pressure. So for the sun becomes about 1,000, or 10 to the 3rd, divided by 3 times 10 to the 8th. So that becomes -8. Let's say that becomes about 3.3. If you keep 10 to the -8 times 10 to the -6 becomes, right? 3.3 times 10 to the -6 was the unit Newton per meter squared. Okay, so this is very, very small. It means that for every square meter, there's a pressure, there's a force of 10 to -6 Newton, or 3 times that, which is very, very, very small pressure, very small force. So that's why we don't feel it. We don't feel that, you know, the light is pushing us, but there is a push from the light. All right. But as I said, there's a device that shows this. You can see that in a lab. In any E&M lab, there is one of those. All right. I think that's everything. But when the surface reflects the light, the momentum transfer and the radiation pressure both double, because you see when you bounce something back, you get more momentum transferred. All right. Any question? All right. That's all. I hope you enjoyed. Have a good night. And if you have any question, I'll be here to answer.
Professor,